Graham's law. So Graham's law looks at the relationship between kinetic energy and temperature, or rather velocity and temperature. So the assumption is that if my assumption is that the average kinetic energy is the measure of the temperature. So if I have two different gases, A and B, and they're both the same temperature, then their kinetic energies will be equal to one another. Now their masses aren't necessarily the same, so I have to be strict and say the mass of A times the velocity of A squared times 1/2 is equal to 1/2 times the mass of B times the velocity of B squared. Well, they both have 1/2 in the equation, so I can cancel them out. And I can play the masses on both sides and the velocities on both sides. So I can think about the proportion. So the mass of A over B is inversely proportional to the velocity of B over A squared. So VB squared over VA squared. Or I can take the square root of both sides and say the square root of the mass of A over mass of B is equal to VB over VA. Basically what it means is the larger my mass, the lower my velocity is going to be, but not in a direct relation, in a proportional relationship. It's going to be in an exponential way, right? So my velocity will decrease exponentially. So it will have a lower average velocity. This is not saying that you're not going to have some particles of gas that are larger than others. So remember our Boltzmann distribution curve. Our Boltzmann distribution curve, which is basically a measure of the number of molecules over the kinetic energy. So if I have a temperature of my gases, basically the average kinetic energy will be right there. That's about the temperature that I have. If I increase the temperature, then the average will increase as well to a higher temperature. I will always have gas particles that are much higher than the average, or ones that are much lower than the average. Here, much higher, lower. But it's the average that you're going to be looking at. And remember that there's a zero value, and that's at 0 Kelvin. So that's when all velocities stop. So if I increase the temperature of both, the mass of A, if it's higher, the velocity of A will still be lower than the velocity of B. It's just they're both going to be a little bit faster. So it's kind of like I'm walking and somebody who's really fast is walking. If we both start to jog, I'll be jogging, they'll be jogging, but they'll still be faster than I will be by the same proportion. So now we get into the part where honors is looking at it, and I'm trying to find some sort of relationship mathematically. So I could ask, how many times faster will an atom of helium, the average atom of helium, travel than argon? So the mass of helium is 4 grams. The molar mass of argon is about 40 grams per mole. So I place argon over helium, 40 over 4, which is 10. So basically the velocity of helium is going to be the velocity of helium, argon, times the square root of 10, which is about 3.2. So on average, your regular helium particle will be traveling 3.2 times faster than the velocity of the average argon particle. If I increase the temperature of both of those containers, as long as the temperatures are the same, both the helium particles and the argon particles will be moving faster, but still, on average, the velocity of the helium particles will be 3.2 times faster than the velocity of the argon particles. It's a proportion. I can also ask, what's the molar mass? Okay, so say that I have a gas that travels 1.17 times faster than carbon dioxide. What is the molar mass? Well, if the gas is traveling faster than carbon, then it has a molar mass that is lower than that of carbon dioxide. So the molar mass of carbon dioxide is 44 grams per mole. So I put 44 over the unknown mass is equal to, the proportion is 1.17. So that's the velocity of this over the velocity of carbon dioxide. So I'd like to get rid of the square root, so I square both sides. So 1.17 squared is equal to 44 over m. So that's going to be equal to 32. So the mass of my unknown gas is going to be 32 grams per mole. So a lot of these things, remember, in chemistry, we're not doing just because we can flex our mental muscles and do calculations using equations. We're really doing it because we want to find out what the identity of an unknown substance is. So one of the easy things, one of the most helpful things or basic things that we can find out is what's the molar mass of my substance. And this is one of the ways that you can figure out the molar mass of a substance.